Hello everyone, this is a problem video for 11.6, so dealing with absolute convergence, conditional convergence, and divergence. So I'm going to do a couple problems from the textbook and then we'll jump to the WebAssign homework to see if there's any hard problems. So the textbook, there's a couple sections of the exercises where it's like, use the ratio test, use the root test, and it kind of tells you what to use. I think it's more useful to for this video to look at problems starting at 31 where it tells you to use any test. So it's unclear what to use. So let's look at 33. When I'm told to test for absolute convergence, conditional convergence, so on, the first thing I do is I usually try and use ratio test first because that's usually the easiest. Okay, remember there's three methods to test for absolute convergence. We have the just definition, we have ratio test, and we have root test. Okay. So I would say ratio test is easiest to use. So that's usually what I start with. All right, so let's try ratio test. Okay, so first thing I need to do is I need to figure out what an plus 1 over an is. Okay. So for this particular series, let's see, an plus 1 will be negative 9 to the n plus 1 over n plus 1, 10, and then this becomes n plus 2, right? Really, what I have here is n plus 1, which is n plus 2. And then I need to divide by an, which means multiplying by the reciprocal. Okay, so that's my an plus 1 over an. Let's simplify and kind of regroup stuff. Okay, so I've kind of regrouped the similar stuff with similar stuff. Now I can simplify easily. Okay, I'm taking absolute values, so any negatives get knocked out, right? Okay, so that's my an plus 1 over an. And now I want to take the limit of that thing as n goes to infinity. Okay, so I'll take the limit of this. Remember, I can bring constants outside the limit. Then I ask myself, what is this limit? Well, that limit should be equal to 1. So I should have 9 over 10. Now, what does ratio test tell me? Okay, the limit's 9 over 10, which is less than 1. Okay, so series is absolutely convergent by ratio test. Okay. Let's try 37 looks interesting. I hope I can do it. All right, absolutely. Let's try a ratio test again. Okay. So when I do ratio test, I get this. Okay. Well, remember we're taking absolute value, so the negatives get canceled. Okay. And then I want to take the limit of this thing, right? So limit of an plus 1 over an equals the limit of that thing. And I want to rewrite that. Let's see if I can copy and paste that real quick. Aha, perfect. All right. Well, that didn't work out very well. Okay. So I want to look at the limit of this thing. Now, the limit of this, maybe it's clear that the limit of this part is 1, but it's kind of unclear what's going on with this. What's the limit of arctan of n plus 1 over arctan of n? That's ambiguous. Okay, so maybe ratio test isn't really working. Okay, so how could I do this? Let's see. How about by definition? Okay, let's try definition of absolute convergence. Okay, so I'm going to take my original series and I'm going to, instead of trying to do ratio test or root test, I'm just going to look at the series of absolute values. Okay, think about the definition of absolute convergence. We say something's absolutely convergent if this series of absolute values converges. All right, so let's see if we can just look at this series and tell if it converges. Well, the absolute value cancels out the negative, right? So the series of absolute values is just this. Okay, and this kind of looks like a p-series, right? I got n squared on the bottom. The only problem is I got this arctan of n thing on top. So what could we do? We could do a couple things probably. Let's see. Well, when we see something that looks like a p-series, what we usually want to do is just comparison test. So let's try a comparison test. What would it, if I'm going to compare this thing to, what am I going to compare it to? Well, it looks like a p-series, right, with just the arctan on top. So maybe I should compare it to 1 over n squared. Okay. Can I compare this directly? Is arctan less than 1? Is it greater than 1? It's hard to say, right? Arctan ranges between negative pi over 2 and pi over 2. So let's use that, okay? No, and you know what? I should have absolute value here, right? So absolute value of arctan, that's going to range between 0 and pi over 2. Okay, so I have this type of inequality. So really, what we can say is absolute value of arctan of n is less than or equal to pi over 2 over n squared, okay? And this is greater than or equal to 0, and this is greater than or equal to 0. So that's all my conditions for a comparison test, right? Okay. So if this series converges, then by comparison test, this series will converge. Okay. The question is, does this series converge? Well, this is just a constant on top, so I can bring it outside. And then what I'm left with is just that p-series. And I know this converges by p-test. So arctan of n's absolute value over n squared converges by comparison test. And remember, this is the absolute value series. This is absolute value of this thing. All right. So that then we can say my original series converges absolutely. So there's a lot to do for that one, and we see that the ratio test didn't really work. So we had to revert back to the definition and then all our previous knowledge from the sections 11.2 through 11.5. Okay. So that's a nice difficult one. Let's now transition to the WebAssign homework and look for any difficult problems there. Okay, looking at problems 1 and 2, those, 1's pretty basic, 2 is kind of a absolute convergence like concept question. So if you read the section and watch the lecture, you shouldn't have any problem there. Number 3, that looks fairly straightforward use of the ratio test. Number 4, I see a factorial there. That's a hint to use the ratio test, and they actually tell you to use the ratio test. Again, that should be a fairly straightforward application. Five should be fairly, let's see, is it? 5 looks like it's going to be probably, okay, 5 would be a good one to do. Let's do 5. This is from the homework now. Okay, so I'm asked to determine whether this is absolutely convergent, conditionally convergent, or divergent. Okay, so let's see, it's an alternating series, but so maybe maybe the series converges, but we want to figure out if it converges absolutely or conditionally. Okay, so let's start with ratio test again. That's kind of our easy thing. So I try my ratio test. Okay. Now you got to be careful when you're doing the n+1 to form the n+1 an+1 correctly. I replace n everywhere I see it with n+1. And so if I'm multiplying 7 by n, okay, I now need to multiply 7 by n+1. Okay, and now I divide by an, which means multiplying by the reciprocal. Let's simplify. Okay, and so that's my an+1 over an when it's simplified. And so the limit of an+1 over an is the limit of 7n+1 over 7n+8. And we know that limit's equal to 1. So what does ratio test tell us? It's inconclusive. I got to do something else. I got to dig a bit deeper. Okay, so maybe that's a good indication to use, or maybe that's a good indication that our series is going to be conditionally convergent. A lot of times when we get this limit equal to 1 in the ratio test or root test, that might mean our series is conditionally convergent. So what do we need to do to show our series is conditionally convergent? We need to show the series of absolute values diverges, and we also need to show the original series converges. Okay. So let's do number 2 first, okay? Look at my original series. Remember I said when we started this thing, it's an alternating series, right? Because of that -1 to the n. So let's try alternating series test. Okay, so what are my conditions? I need an+1 less than or equal to an, and I need limit an goes to 0, right? Where what's the an in this case? Well, let's write bn to avoid any confusion. So what's the bn, right? I can rewrite this series as like -1 to the n 1 over 7n plus 1. And this is my alternating part, and this is my numerical part. And really, this is the bn's that I want. So I need to check these two things. Are the terms decreasing, these numerical terms? Well, yeah, right? When n gets bigger, this fraction gets smaller. Okay, I'm going quickly here, but you would need to show that a bit more methodically on a test. And then, does the limit of those terms go to 0? Well, yeah, as n gets big, this fraction goes to 0. Okay, so that's everything for my alternating series test. So this converges by alternating series test. Okay, so the original series converges. All right, so I'm halfway there. Next, I need to do, let's see. So we did 2. Now I need to do 1. Does the series of absolute values diverge? Okay, so I consider the absolute values. Okay, when I do that, the series just becomes 1 over 7n plus 1. Does this series converge or diverge? Well, it's gonna diverge. And this, showing this diverges would be interesting. It looks to me like limit comparison test. I should compare it. I should use limit comparison test with the series 1 over 7n. Or maybe a better series would be 1 over n plus 1. That should work as well. Okay, this series, this is basically just a harmonic series, right? Just kind of shifted a little bit. So this diverges. And if we wanted to be technical, we could show that this diverges by limit comparison test as well, comparing it to 1 over n. Okay. The important thing to know is that this diverges. And then I do limit comparison tests between these two series. Okay. So recall how that would work. I would take 1 over 7n plus 1 and divide it by 1 over n plus 1. And the limit of that equals 1 over 7. So the limit is a positive number greater than 0. So what does limit comparison test tell me? These do the same thing. These series do the same thing. Since 1 over n plus 1 diverges, that implies 1 over 7n plus 1 diverges by limit comparison test. So I've shown my two things. I've shown that the series of absolute values diverges, and I've shown the series of the original series converges. So that's the very definition of conditional convergence. And that's how you would have to show it on a test. Okay. Number 6 looks very similar to the problem we did up here, number 37. Okay, so if you're having a problem on number 6 on the homework, go back to this thing. Okay, number 37 from the homework. Let's see, number 7. It's kind of similar to this one we did here, this number 5. So use that. Number 8, okay, I see everything's to the power n. That's a hint to use the root test. Okay. Number 9, they tell you to use the root test. And doesn't look too complicated there. Let's look at number 10 real quick. Number 10 looks interesting. I have 6, in my problem, I have 6 times 1 over 1 plus n into the power n squared, okay? So let's kind of make this a bit easier for us. I got a constant, right? I can bring the constant outside the series, no problem. And so now I want to figure out if this series is absolutely convergent, conditionally convergent, what's going on? Well, what's the deal with n squared? You know, if it was n, I could use root test, right? But I have n squared. Well, that's no problem. Just think of n squared as this to the power n the power n. It's the same thing, right? So I have a power n here. So let's try, now that indicates root test, right? So let's try root test on this thing, okay? So I do the nth root of absolute value of an, where this is my an would be this whole thing. So okay, so I do the nth root. This nth root is going to cancel with this kind of outer n, right? And I'm left with this. And you might say to yourself, hey, that doesn't really help us, right? Because now I need to take the limit of this thing, and I still got this power of n. You know, what is that limit? I can't do that limit. Well, actually, you can. This is a famous limit, and this is, maybe you don't know it off the top of your head, but this is a very famous limit. This is the very definition of the number e. The limit of 1 plus 1 over n to the power n. That limit converges, and it converges to that number e, which is, whatever, I always forget, 2.718, something like that. Okay. So this is e. Okay, so I did my root test, and the limit is e. Okay, and e is greater than 1. So what does that tell me about my series? My series is divergent. Okay, so interesting problem there. Number 11 looks fairly straightforward. Everything looks fairly straightforward there. Let's look at number 12. I have n factorial squared over k times n factorial. And I'm asked for what values of k is the series convergent. Okay, that's an interesting problem. Okay, so let's try, I see factorials. Maybe that's a clue to do ratio test. Let's try ratio test, okay? And let's leave k just kind of as an unknown for a second, okay? What's an plus 1 over an? Well, that would be n plus 1 factorial squared over k times n plus 1 factorial. Then I'm going to divide by an, which would be looking fairly complicated. All right, let's try and simplify. Okay, let's start with n plus 1 factorial squared. And let's go ahead and put the kind of similar stuff over similar stuff. I would pair that up with n factorial squared. And then I would have kn factorial over k n plus 1 factorial. And now let's simplify. And let's start by simplifying the factorial. And again, you can check out my factorial simplification video. I don't know if I put it on web courses yet, but it is on YouTube. Okay, so it's already posted on YouTube. So check out the YouTube channel if I haven't posted it already. I forget if I did or not. But let's simplify the factorials. How do these factorials simplify? Well, remember that, let's see, n plus 1 factorial, what is that? That's n plus 1 times n minus 1, dot, dot, dot. So really, I could actually think of n plus 1 factorial as n plus 1 times n factorial, right? Okay, same thing, and then I'm squaring that. And then I'm dividing by n factorial squared. okay? And then I got this other stuff. Okay. But let's focus on the factorials for a second. Basically what I have is I have AB squared over B squared. How can I simplify that, right? Like this is my A, this is my B, and then I got the B again on the bottom. How does this simplify? Think about this simpler form. That simplifies as just A squared, right? Because I can split the top up like this, and then I got B squareds on top and bottom. The B squareds cancel, and I'm just left with A squared. Okay. So this factorial stuff should just simplify as n plus 1 squared. Okay. All right. And then now let's look at this stuff here. Okay. I got 2n factorial, or no, excuse me, that's not 2, that's a k. I got kn factorial over k times n plus 1 factorial. So let's simplify the bottom, okay? K times n plus 1 is kn plus k factorial, and then I got kn factorial, okay? So how would that simplify? Well, that should simplify, remember what's the bottom? Kn plus k factorial is kn plus k, kn plus k minus 1, and then it eventually gets down to kn, right? And then from here on out, everything's going to cancel with the kn factorial on top, right? Because kn factorial is kn minus 1, okay. So from there, everything's going to cancel, and I'm going to be left with this stuff, which is what? I'd have 1 on top. On bottom, I would have kn plus k. Kn plus k minus 1, and so on until I get to kn plus 1. Now, how does that simplify with everything up there? Okay. This is about as simple as I can make it. And let's just kind of rewrite it real quick. So I've just rewritten a bit neater, and this is what we get when we simplify. All right. And now the question is asking, what are we doing? We're doing ratio tests, right? And the problem is asking for what positive integers k does the series converge? So we're trying to figure out when is the limit of this thing going to be less than 1? Okay. So let's just start plugging in some integers and see what happens. So a logical place to start would be at k equals 1, right? So what do I get when I plug in k equals 1? I get n plus 1 squared. And then what does this fraction become? Okay. Notice that this is like an increasing list of numbers, right? We're starting at kn plus 1 and going to kn plus k. So if I plug in 1 for k, the range is from n plus 1 to what? N plus 1. Okay, well, that's just the same number, right? And I don't have n plus 1 squared. I'll just have n plus 1, okay? So my terms left over after the factorial cancellation, like there's none over here. So basically all I have is n plus 1. And then when I simplify that, okay, I got n plus 1 squared over n plus 1. That's equal to n plus 1. Okay. So what's the limit of this? This is my an plus 1 over an. What's the limit of that? Well, it's equal to infinity, which is definitely greater than 1. So when k equals 1, my series diverges. Okay, so I don't want to include k. All right, so let's try k equals 2 now. Okay, so we did k equals 1. All right, so let's plug k equals 2 into this thing. Let's copy. So let's plug k equals 2 into this thing. So I plug in k equals 2. Okay, I still have n plus 1 squared. Then when I plug in k equals 2, my range on the bottom would be from what, 2n plus 1 all the way to 2n plus 2. Okay, well, that's just two numbers, right? This is 2n plus 2 times 2n plus 1. Now, here's where it gets interesting. Notice that we can factor this one as 1 over 2 times n plus 1, right? And I got 2n plus 1. Okay. This n plus 1 cancels with one of those. And I have n plus 1 over 2 times 2n plus 1. Now, what's the limit of this? The limit of this is equal to 1/4, which is less than 1. So when k equals 2, my series is going to be absolutely convergent, okay? So the question was asking for what values of k does my series converge? Well, it starts converging when k equals 2. So my series is going to converge when k is greater than or equal to 2. So that concludes that problem. I think that's probably the hardest problem on the homework. 13 looks fairly basic. And then 14, 15 are review problems. So that concludes this problem video.